But don't let the name throw you. It's still the same equilibrium constant we use. But excuse me. Talk to me.
It's Ryan! The bomb is in play!
What? I thought that middle-aged goth chick from NCIS was working on it. What happened to her?
I'm getting hacked.
Oh, Portsky?
No, this is major.
NSA's putting up firewalls.
Arlo's working on getting through them right now. The president can't lock down every media outlet.
That information that was false and fake and never happened got released to the public. As far as BuzzFeed, which is a failing pile of garbage.
Oh, God. So last time we looked at the relationship between acid dissociation constants and pH. Today we're going to look at base dissociation constants and pH. So to start with, just like every Bronsted acid followed the same generic reaction and had the same generic type of equilibrium constant, which we called Ka, every base that follows the Bronsted-Lowry behavior has the same generic type of reaction, which is the base, whatever it is, reacts with water to give you the conjugate of that base, which is just the original formula plus a H plus somewhere, and hydroxide. So if every Bronsted base follows the same generic type of reaction, it's going to have the same generic type of equilibrium constant. The conjugate acid times hydroxide over the original base. Remember, we don't include liquids in equilibrium constants, or solids for that matter. So before with acids, we gave it its own special letter Ka and called it the acid dissociation constant. Here we're going to give it this equilibrium constant its own special letter B and call it the base dissociation constant. And any calculations we do with Kb and pH are really similar to the ones we did with Ka and pH last time. It's just that when you're dealing with a weak base, there's one extra little thing you have to deal with. For example, let's say you have a 0.25 molar base solution with a pH of 10.3. To find the Kb of that solution, again, we're going to start with an ice table. And like last time with acids, we're assuming this concentration is the formal concentration before any of this dissociation stuff happens. So our initial concentration of base is whatever's given in the problem. Liquids, again, we ignore, so we don't bother with those. And if we assume this is the formal concentration, there shouldn't be any BH or BH plus. And if we ignore autoionization for the sake of convenience, like we talked about last time with acids, there should be zero hydroxide as well. So our change is going to shift to the right since we have zero on something on the product side. You got to form some product. So you're going to lose X amount of base, gain X amount of each product, and it's minus X and plus X because everybody's 1 to 1. So at equilibrium, it's our original concentration minus X for the base, X and X for each product. So from here, we go to our expression of Kb and plug in what we know. We know the concentrations of both products are X, so X times X gives you X squared. On the bottom, our base concentration is 0.25 minus X. So to find Kb, we need to find X. And last time what we did is we found X straight from the pH because there hydronium was part of our acid reaction and pH is related to the hydronium concentration. That's minus the log of the hydronium concentration. But in this case, X isn't equal to the hydronium concentration, it's equal to the hydroxide concentration. So before we can find X, one way to do it, or at least the way I like to do it, is we need to convert our pH to a POH, and that'll give us the hydroxide concentration. Because remember, for any solution, the pH and the POH add up to 14. So if the pH is 10.3, the POH should be 3.7. Now we take that POH and plug it into our POH equation. Solve for X, that gives us a value of 2 times 10 to the negative 4. So we take that value of X, plug it into our expression of Kb, and that'll give us a Kb of 1.6 times 10 to the negative 7. So if you compare that problem to the one we did previously, where you found the Ka of a solution of a known pH, it's really the exact same type of problem, and you solve it the exact same way, except with a base, there's that one little additional thing you have to do. You have to convert a pH to a pOH. Because here the X isn't directly related to the hydronium concentration, it's directly related to the hydroxide concentration. Now let's look at a problem where you find the pH from Kb. Let's say you want to find the pH of a 1.3 molar solution of ammonia, and we know ammonia's Kb is 1.8 times 10 to the negative 5. Again, you start with an ice table, assuming this is the formal concentration, and we usually do. The initial concentration of ammonia will be 1.3. Water, we don't care. For our two products, 0 and 0, because we're ignoring autoionization. So all of our coefficients are 1, so we should lose X amount of ammonia, gain X amount of each product. So at equilibrium, it's 1.3 minus X, and X and X for each product. And from this point, just like before, we take rho E and we plug it into our expression of Kb, along with our known value of Kb. And when you do that, you have everything you need to solve for X. So you solve for X. Again, we're going to assume that approximation is going to be valid in this case, and that initial concentration is approximately going to be the same as before, which we talked about last time, and in previous videos when we talked about just equilibrium in general. So you plug 1.3 in at the bottom, then that gives you an X of 0.0048, which should be our hydroxide concentration. And like we talked about in the equilibrium chapter, it should obey the 5% rule, and it does. So again, our approximation is okay. So if that's our value of X, then again, before X was equal to the hydronium concentration, but just like our previous problem we just did today, X is our hydroxide concentration. So if you take the negative log of 0.0048, you're actually finding the pOH. But again, that's no big deal, because for any solution, the pH and the pOH have to equal 14. So if the pOH is 2.3, the pH must be 11.7, which is in the basic region. So again, barring a calculation error, we're at least on the proper side of the pH scale. So again, you compare this problem to the one we did in the previous episode, where you found the pH of an acid solution, where you knew the acid and you knew the Ka. Again, it's the exact same type of problem. There's just one little additional thing we have to do. But in both cases, whether you're finding Kb from pH or pH from Kb, it's just you have to do a pH-pOH conversion. And again, just because X is related to the hydroxide concentration in our ice table, not hydronium like it was before. But otherwise, it's pretty much the exact same type of problems. So we'll stop there, and we will talk about something else next time. Bye.
Isolate the node and dump them on the other side of the router.
I'm trying. It's moving too fast.
Oh God, are they just typing random shit on the keyboard again?